Continuing in our probability chapter, we now explore two rules for calculating the probabilities of compound events: the addition rule for events that include the word or, and the multiplication rule for events that involve the word and. We start with the addition rule as a tool for finding the probability of A or B, which is the probability that either event A occurs or that event B occurs, or that they both occur as the single outcome of a procedure. The word or should be associated with addition of probabilities. We will also look at the multiplication rule, which will be used for finding the probability of A and B, which is the probability that event A occurs and that event B occurs. The word and should be associated with multiplication of probabilities. Let's define a compound event. You might recall that we defined a single event as an outcome of a procedure that can't be broken down into simpler parts. A compound event, on the other hand, is any event combining two or more simple events. For example, we said in the roll of a single six-sided die, rolling the number 2 would be considered a simple event because there's only one way to do that, but rolling an even number, for instance, would be considered not single. In this case, we now know the word is compound. Rolling an even number would be possible by rolling a 2, a 4, or a 6. So there are two or more simple events that would constitute rolling an even number. In the addition rule, P, parentheses, A or B, close parentheses, will stand for the probability of A or B, which is the probability that in a single trial, event A occurs or event B occurs, or they both occur simultaneously. Again, this is in a single trial. To find the probability of A or B, we're going to add the number of ways that event A can occur to the number of ways that event B can occur, but we're going to do so in such a way that each outcome is counted only once. We want to make sure that we're not counting any outcomes multiple times. Therefore, the probability of A or B is equal to that sum divided by the total number of outcomes in the sample space. Here we have the formal addition rule. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which refers to the overlap. So in the probability of A, we're going to consider all the outcomes that satisfy event A. In the probability of B, we consider all the outcomes that satisfy event B, but there may be some outcomes that satisfy both event A and B, and they have been counted twice. They've been included in the first probability calculation, and they would have also been included in the second. So by subtracting the overlap, we're ensuring that nothing is counted more than once. Let's define what disjoint or mutually exclusive events are. Events A and B are said to be disjoint or mutually exclusive if they cannot occur at the same time. That is, they do not have any overlap. Here's an example of disjoint events. Let's say that event A is randomly selecting someone for a clinical trial who is male. Event B is randomly selecting someone for a clinical trial who is female. Then the person cannot satisfy both events A and B because there is no individual who is considered both male and female at the same time. Keep in mind, we're not talking about gender, which is identity. We're talking about physical sex. So male and female do not have an overlap in this case. Events that are not disjoint, meaning they do have an overlap, share at least one common outcome. For example, event A, randomly selecting someone taking a statistics course. Event B, randomly selecting someone who is a female. Clearly, it is possible for someone to be taking a statistics course and also be female. So any females taking statistics courses would satisfy both events. So here's a summary of the addition rule. To find the probability of A or B, first we want to make sure anytime we see the word or, we're associating it with addition of probabilities. To find the value of the probability of A or B, we add the number of ways that A can occur to the number of ways that B can occur, being careful not to count any outcomes multiple times. Let's move on to the complementary rule. Complementary events are events that do not share any common outcomes, and yet together they cover the entire sample space. So they cover all the possible outcomes of a procedure, but with no overlap. So we learned in our last lesson that this A with a little line segment on top is referred to as a complement, or not A, and it is the set of all the outcomes of a procedure that do not satisfy event A. Common sense then dictates the following principle. We are certain, meaning there's a probability of exactly 1, that when we run a procedure, either event A occurs or it does not occur. Therefore, it follows that the probability of A or A complement is exactly 1. And that makes sense. Whatever the outcome, it either will satisfy event A or it won't satisfy event A. It's a certainty that one of the two is going to happen. Because events A and A complement must be disjoint, we can use the addition rule to express this principle as follows. The probability of A or A complement is equal to the probability of A plus the probability of A complement, which is equal to exactly 1. And that makes sense. This probability would consider all the outcomes in the sample space that satisfy event A, and the second probability includes all of the outcomes that don't satisfy event A, and together they cover everything in the sample space, every possible outcome. So here's some alternate versions of the complementary rule for probability. We already saw the first one. Probability of A plus the probability of A complement is exactly 1. We also can say that the probability of A complement is equal to 1 minus the probability of A, or vice versa, probability of A is equal to 1 minus the probability of A complement. This is actually a very simple, straightforward relationship, and we'll look at some examples to show you why this makes perfect sense. Let's look at this example from your textbook. Based on survey results from the Consumer Technology Association, the probability of randomly selecting a household in the United States and getting one with a smartphone is 0.87. So the probability that a household has a smartphone is 0.87. If a household is randomly selected, find the probability of getting one that does not have a smartphone. And I think we can probably do this without having to fast forward to the next slide. If the probability of having a smartphone in a randomly selected household is 87%, then the probability that a randomly selected household will not have a smartphone would be 1 minus 0.87, or 13%. And here it is. Using the rule of complementary events, we find that the probability that a randomly selected household does not have a smartphone is equal to 0.13 by subtraction. Now let's move on to the multiplication rule. Let's look at the notation first. The probability of A and B is equal to the probability that event A occurs in a first trial and that event B occurs in a second trial. Unlike the addition rule, this rule necessitates 2 different trials, 2 different outcomes coming from 2 different trials. So the addition rule, the probability of A or B, was looking at a single trial and having that outcome satisfy A or satisfy B or satisfy both at the same time. The multiplication rule for probability of A and B does require 2 separate trials. Now let's look at the probability of B given A. This little vertical line segment stands for given that. So the probability of B given A represents the probability of event B occurring after it is assumed that event A has already occurred. So probability of B given that A has occurred. Let's look at the multiplication rules using some intuition, just some thought, and then we'll look at the formal rule in just a moment. To find the probability that event A occurs in one trial and that event B occurs in another trial, multiply the probability of event A by the probability of event B, making sure that when we calculate the probability of event B, we are assuming that event A has already occurred in a first trial. We're going to see why that's important as we look at some examples where selections are being made with replacement and without replacement. Here is the formal multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A. So again, this means that we're going to multiply the probability of event A occurring in a first trial by the probability of B occurring in a second trial, given that we have knowledge that event A has already occurred. Let's explore the idea of independence. Two events, A and B, are said to be independent if the occurrence of one does not affect the probability of the occurrence of the other. So, for example, whether A has occurred or not, it would have no bearing on the probability of B occurring. Several events are independent if the occurrence of any does not affect the probability of the occurrence of any of the others. If A and B are not independent, they are said to be dependent. Let's look at an example. 50 test results from the subjects who used drugs are shown below. We have 50 people who are known to be drug users, and they are being tested. We have, of the 50, 45 positive test results, and we have 5 negative test results, for a total of 50 test results. If 2 of these 50 subjects are randomly selected with replacement, find the probability that the first selected person had a positive test result and that the second selected person had a negative test result. Very important that we pay attention to these words, with replacement. That means that after the first person is selected and we record whether the result was positive or negative, that person then gets returned to the group of 50, making it possible for that person to be chosen at random a second time. In part B of this problem, we're going to repeat that calculation, but we're going to assume that the 2 subjects are selected without replacement. So once the first person is selected and we make note of whether the test result was positive or negative, that individual will not be returned to the group of 50, so there will only be 49 people left to choose from. So let's look at part A of this problem. If we select a person at random and we record whether the person tested positive or negative, in our first selection, we have 50 people to choose from, and 45 of them have positive results. So the probability of getting a positive result would be 45 out of 50. Now we're going to make note of that person, and then we're going to return the person to the group of 50. So then we go and make a second selection. We have 5 negative test results among the same 50 people, so the probability that the second person selected will have a negative test result would be 5 out of 50. Remember that this is an AND problem. We want the first person to test positive and the second person to test negative. Therefore, we're going to use the multiplication rule and multiply these 2 probabilities together. So the probability of getting a positive test result in the first selection and then a negative test result in the second selection would be 45 out of 50 times 5 out of 50, which is 0.09. Now let's repeat the calculation, assuming that there was no replacement. So we have 1 person chosen at random. We want that first person to have a positive test result. That person does not go back to the group, and therefore we only have 49 people to choose from for the second selection. And let's look at the breakdown of the calculation now. So the probability that the first selected person has a positive test result is still 45 out of 50. But once we take out that positive test result, it does not go back to the group. So we only have 49 people left to choose from. And of those 49 test results, we want the second selection to be negative, and there were 5 negative results left. And so that probability is 5 out of 49. Once we multiply these two probabilities, we find that the probability is 0.0918, slightly larger than the one we found in Part A. Sampling happens all the time in statistics. That's actually the backbone of statistics, to examine a sample from a population that we have some interest in, examining it closely, looking at what we see in the sample, and then making those observations relate back to the larger population that we have an interest in. In the world of statistics, sampling methods are critically important, and the following relationships hold. Sampling with replacements are selections that are going to create independent events. Why? Because if we make a selection and we return that selection to the sample for a possible future selection, every future selection is like a do-over. Nothing has changed with the possibilities of what we select. However, when we sample without replacement, as soon as we make a selection, that selection is no longer eligible to go and be selected again, and it's changing and shrinking the possibilities of what we can select, and so that's going to create dependent events, dependent selections. We've looked at the 5% as a threshold in previous sections. Here we're going to look at the 5% guideline for cumbersome calculations. Here's what it says. When sampling without replacement, if our sample size is no more than 5% of the size of the entire population that we are interested in, then we can treat those selections as being independent, even though they actually are not. Let me say this again. If we are sampling without replacement, we can make an adjustment and treat it as if we were making selections with replacement, as long as our sample size is very small, meaning no more than 5% of the size of our entire population of interest. This will make it easier for us to calculate some probabilities when we have very large populations and very small samples coming from them. Let's look at the following example as an exemplification of this rule. In a recent year, there were 130,639,273 full-time employees in the United States. If one of those employees is randomly selected and tested for illegal drug use, there is a 0.042 probability that the test will yield a positive result, indicating that the employee is likely using illegal drugs, based on data from Quest Diagnostics. Assume that 3 employees are randomly selected without replacement from the very large population of 130,639,273 employees in the U.S. Find the probability that the 3 selected employees all test positive for drug use. Anytime we see wording like this, all, that indicates an and situation. If we want 3 individuals to be selected at random and we want all of them to test positive, that means we want the first one to test positive and the second to test positive and the third to test positive. So this is an and problem that will require multiplication. Because the 3 employees are randomly selected without replacement, the 3 events are technically dependent. But because our population is so large and our sample size is so small, 3 is certainly less than 5% of 130,639,273, we can actually treat our 3 selections as if they were indeed independent, as if we did have replacement. And I think you can see why such an adjustment is not going to make a big difference. So, probability that all 3 employees are going to test positive is the probability that the first does, and that the second does, and that the third does. And so we get a very, very, very small probability of 0.0000741. The principle of redundancy is used to increase the reliability of many systems. We're making a turn here into something seemingly unrelated, but we're going to tie it back in just a moment. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. It's a backup. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. Think about having multiple engines on an airplane, for instance. If one engine fails, the remaining engines can still carry that flight to safety if needed. Let's look at an example where we look at the principle of redundancy, and let's see how it ties to the multiplication rule. The Seagate hard drive model has a failure rate of 2.89% in a year, based on data from Backblaze Inc. Part A of this question. If your computer has only the Seagate hard drive, what is the probability that it will work for a year? Part B is going to ask, if your computer has 2 of the Seagate modeled hard drives, what is the probability that at least one of them will work for a year, meaning your computer will continue working for the year? So in part A, we have a single hard drive. If the failure rate is 2.89%, and let's write this as a decimal, 2.89%, let's move that decimal place 2 spaces to the left, is written as 0.0289 failure rate, or the probability that it will fail. Then the probability that it will not fail would be 1 minus 0.0289 using the complement rule. So the probability that the single hard drive will not fail is 0.971. Pretty good. However, I would hate to have almost a 3% chance of having the hard drive fail in a given year. Part 2, we're going to assume that we have 2 independent hard drives. So we have one as a backup. The probability that the computer is going to work, meaning it has at least one working hard drive, would be equal to the probability that both hard drives fail together, subtracted from 1, right? So for the computer to keep working, we just need at least one of those hard drives to continue working. So the complement of having at least one working is that they both fail. So the probability that they both fail would be 0.0289 multiplied by itself, 0.0289. That product subtracted from 1 would give us 0.999 probability that at least one of the 2 hard drives will be working at the end of the year, and that is a much, much better probability that things will be well. So the interpretation here is that with only one hard drive, there is a 0.0289 probability of failure, but with 2 independent hard drives, there's only a 0.001 probability that the computer will not work. And so using 2 hard drives instead of just one drastically reduces the risk of failure. By using 2 independent hard drives, we avoid the probability of serious failure, and this redundancy model is used in the real world all over. Think about things having to be backed up, systems that have to be backed up if something fails. And lastly, let's summarize what we've seen in this section. The addition rule is used to compute the probability of event A or event B occurring in a single trial. We looked at the fact that we have addition here and that we want to make sure that no outcome is counted twice. With the multiplication rule, we're finding the probability of A and B, which is the probability that event A occurs in the first trial and that event B occurs in the second trial, with the knowledge that event A has already occurred.